Good morning, students. Today we will be studying about the relationship between the modulus of rigidity, Young's modulus, and the Poisson's ratio. Okay, so we are going to see the relationship between the eta, y, and k. Okay, and sigma, Poisson's ratio. To consider this, we are going to now consider a cubical vessel, and we are going to consider that the cube is made of a unit volume and has a unit area. Okay, so we are going to consider a cube with a unit length. Okay, with a unit length and unit area and unit volume. Okay, and we are not going to consider the bulk modulus over here. Okay, so bulk modulus is not going to be considered. Okay, only the relationship between the modulus of rigidity, Young's modulus, and the Poisson's ratio is going to be studied in this particular video. Okay, so let's assume that, let me draw the diagram of a cube, okay, which is made to undergo a shearing stress, okay, and that is applied a force here, which is like that. Okay, you have a cube. Imagine that this is a cube, and you are going to apply a tangential force in this. Okay, so the body gets sheared like this. Okay, so let me draw the diagram. So this is A, B, C, and D. Okay. This is E and F. So when I apply a force along this direction, when the force is applied along this direction, the A will never be in A, but it will shift to A dash. Okay, it will shift to A dash by a length L, and C will B dash. See? B will get sheared to B. Okay, we will get distance N. Okay, so the shearing stress can be measured in terms of the elongation that it has undergone L, which we call it as a linear stress, or a, which can be measured in terms of tension. In Poisson's ratio, we need that Poisson's ratio is nothing but the ratio of the lateral strain beta to that of the linear strain. Okay, so it is a strain tangential. So undergo change in length on one side, the body will undergo a change in the length, and the same body will undergo decrease in the diameter. Okay, so we are going to measure the linear strain portion, okay, or a tangential strain, which is caused to a tensile stress that is being applied by a force which is acting along this direction, which in turn produces an elongation L on these two sides. Okay, so in one side we have to measure the elongation, how much it has gone elongated due to the shearing stress that is being applied by this force. That is the aim of this particular class. Okay, so our ultimate aim is we are going to find the modulus of rigidity, and then we will connect it with the Young's modulus, and then we will connect it with the Poisson's ratio. Okay, and you already know that Poisson's ratio is related to 1 by y is equal to 1 by alpha. Okay, this relation we derived it already. Okay, so this is strain, no? Change in length by original length, which is related to Poisson's ratio. So this equation we will come back later on. Okay, now our ultimate aim is how much this has sheared. Okay, so in order to take the diagonal, okay, dB, okay, and how much this diagonal DB has elongated to the new diagonal DB dash. Okay, so the new will be equal to this way. The new diagonal will be a little elongated than the original diagonal. Okay, so when this is sheared along this side, okay, what happens is there is a compressive force that acts along the other opposite side, which is in a perpendicular direction. Okay, a tensile stress is being applied along this direction. The simultaneously a compressive force is acting along the direction of AC. Okay, in AC direction, you have a compressive force elongated than the compressive force acting along it. Okay, in along the diagonal DB, okay, along the diagonal DB, tensile forces applied, which produces elongation. Okay, this will produces along AC, the diagonal is getting compressed. Again, it is enhancing this elongation. Okay, so we need to calculate the extension that is produced along DB, and the extension is that is being produced due to the compression along AC. So together we need to add up these two to find the total elongation. So before going into it, let me first find out. Okay, we all know that the modulus of rigidity is given by this formula. Okay, modulus of rigidity, eta is what? You have the shearing stress here, shearing stress divided by shearing strain. Okay, now what is the shearing stress? It is force per unit area, isn't it? Force per unit area. Area is nothing but L square, but it is unity. Okay, so and down one is we need to find the shearing strain. Okay, due to the force that is being applied. Okay, resulting in the shearings or shearing stress along this side. Okay, so shearing strain would be the change in the length. Okay, by original length, isn't it? Okay. So this is a unit area. Okay, since we are considering, since the area is unity, I will put A is equal to 1. Okay, and also the force is equal to the force applied. Okay, the force applied is equal to the tensile stress. Okay, the force is applied in the form of tensile stress. So I will put this notation as T. Okay, so the numerator will become, okay, eta will become, okay, eta will become, okay, F, I am going to replace it by, okay, F is equal to T, okay, tensile stress. So the numerator will become T by 1, okay, it will be T by unit area 1, and this will remain as L by capital L. Okay, so this one, again, I'm going to write it as just T into, take the L on the numerator, TL by L. Okay, so eta is going to be T into L by L. This will be our first equation. We will come back to this first equation later on. Okay, now we will see our aim is to find this elongation. The shearing strain will be in terms of the elongation that is produced, okay, due to the force that is being applied, which in turn produces the tensile stress along one side and compressive stress on the other side. So there is elongation due to the tensile stress acting along this side and a compression. This also is getting compressed and adding up to the addition of the length. Okay, so we need to add up both the elongations together. Okay, and then we will come back and substitute that value of L in this equation. That is our final aim. Okay, so now let's see how much it has gone elongated. Okay, So shall I rub this figure? Okay. Now we need to find the increase in the length of the diagonal. Okay. Our aim is we need to find the increase, okay, in the length of the diagonal. In the length of the diagonal dv. Okay, that is our diagonal. No? How much it has gone, how much it has increased, we need to find out. Okay, that can be find out due to two factors. Okay, so that will be the increase in the length okay, due to the tensile stress, due to the tensile stress is equal to, okay, diagonal dB into, okay, the tensile force that is being applied, tensile stress that is being applied, that factor also has to be added with the elongation, the tangential strain that is adding up to that length. Okay, now linear strain T alpha has to be added. Okay, and also we have to write the decrease in the length. Okay, there is a compressive force which is producing a again an increase in the length. Okay, so we need to add the increase in the length due to the compressive force acting along AC, okay, is equal to dB, okay, along AC direction. Do you remember this figure? Okay, A, B, C, D, okay, okay, along D and B, okay, along AC, I think this is C. Along DB, there is an elongation, okay, and along AC, it's compressing. But again, that compression will also results in the adding up of the elongation. Okay, AC side is compressing, but again, it will enhance that elongation. Therefore, I've written the increase in the length due to the compressive force acting along AC will be equal to dB, okay, is equal to D into B into T into beta. Okay, beta, there is a decrease in the diameter, but that is increasing the length of the diagonal. Okay, so that factor is this one. Okay, now these two factors have to be added for the total extension along dB. Okay, so the total extension is equal to the total extension will be the addition of both the factors, isn't it? Both have to be added up. So adding up this equation and this equation, okay, so it is dB on both the sides same, okay, T also same, okay, it will be alpha plus beta. Now we need to find what is dB from the figure, okay. So one more time, let me draw. Okay. It is A, B, C, D, okay. This is a diagonal, okay. And this side is a unit length, okay. So this will become root 2 into L by Pythagoras formula. You will add up this L square, okay. It will become 1 L square plus 1 L square, it will become 2 L square. So it will be dB is equal to root 2 into L, okay. So since dB is equal to root 2 into L, substitute that, okay, this extension, total extension will become now, okay, the total extension will be equal to, okay, dB. I'm going to substitute root 2 L on this factor. Okay, it will become root 2 L into T into alpha plus beta. Okay, now let's put this as equation number. This is a total extension along dB. Okay, let's me put this as equation number 2. Okay, now this extension dB, okay, has ultimately resulted that B to go to B dash. Okay, so this is the length. This extension has now have increased the length from B to B dash as L. Okay, so we need to find what is L. Okay, so how to find the length to which it has extended? Okay, so that length is in terms of, we need to find the extra length it has extended, isn't it? So draw a perpendicular along the side. Okay, so when you draw it, okay, put this as P. Okay, so up to this is the same distance, isn't it? dB is same as dP. Okay, the distance of dB and dP is same. Okay, the distance of dB is equal to the distance of dP. The extra length is the excess or the increase in the length, okay, is nothing but PB is equal to PB dash. Okay, this is the extra length, okay, which has to be measured in terms of L. Okay, only we know that this is equivalent to L, but this is the actual extra distance. Okay, so this L has to be measured between this triangle. Okay, so we are going to draw this figure again. Okay, the extra length is actually PB dash, but we know that B to B dash, it has gone to L. Okay, so we need to take this as a triangle and we need to find the, because it has sheared through an angle. Okay, and now the angle here is 90 degree. Okay, and so if you take another, okay, another cube like this, okay, so here also the angle may not be 90, it may be 88 or 89. It must have gone through a very small angle, okay, sheared. But let's approximately take it as 90 degree itself, because the amount to which it has sheared may be very, very minimum, and this length, although in the board it is little looking bigger, but that length also may be very, very few millimeters. So approximately, we are not going to take it as 88 or 89, but we are going to take it as 90 degrees. So if I'm going to take it as a 90 degree, I'm going to take this entire thing as 90 degree. In that case, this half will become 45 degree and the other one will become 45 degree. Okay, so we need to find what is PB dash. That is our next aim. Okay, so I will write this again as, okay, extension D. Okay, this point. Okay, the extension of the diagonal DB is equal to, okay, extension is equal to PB dash. Okay, I will put this 3. Okay, we are going to come back to this equation. Okay, on this side it's going to be this value, and this one we are going to find now. Okay, PB dash, we are going to find it out. Okay, so this increase in the length PB dash has to be found out from this region. Okay, so how to find it? So let's draw this figure again one more time properly in a big way. Okay, see here, I'm dropping a perpendicular, and see this is a this one DB. Okay, this is DB dash. It is increased to a length L. Okay, to find that, draw up to this is the same distance. Okay, these two distances are same. This is the extra distance. Okay, so draw a perpendicular from this B, it will be P. Okay, now in this one, okay, the angle here will be 45, because this entire thing here it is 90 degree, here also it is approximated to 90 degree. So two halves, I'm taking it as 45, 45. So in this triangle, we need to find PB dash. So how to find the PB dash? Okay, you know that. Take it in a big form. Okay, So take the cosine angle of 45. Okay, cos 45 you need to take. So theta is here. Okay, B dash. Okay, this is L. Okay. So what is cos 45? This is cos, isn't it 45? Okay, theta is 45 degree. We need to take the cos 45 degree over here. Okay, cos 45 is, this is the base. Okay, this is a base, this is a perpendicular, this is hypotenuse. Okay, so cos angle is nothing but, okay, base by hypotenuse, isn't it? So base here is PB. Okay, PB. Okay, so cos 45 degree. Isn't it? B dash is equal to cos 45 degree into BB dash. Okay. What is cos 45 degree? It is 1 by root 2. Okay. So 1 by root 2 into BB dash is L. Okay. Here it has not only undergone a length increase in the extension alone, but along with an angle it has sheared. So we cannot neglect the cos factor through which it has gone sheared through an angle. Although it's less, we have approximated to 90 degree, we cannot totally neglect the angle part. So that is why we have to take it with the angle part. So it is cos 45 degree we have involved. Okay. So root 2 into what is BB dash? The length, extended length here. Okay. So PB dash is equal to, PB dash is equal to, I can write it as L by root 2. Okay. Write it here. Okay. Therefore, PB dash is equal by root. This will be our. So come back to this equation now. Okay. You have one part which is equal to dB, which we got it from equation 2. We have PB dash on the right side, which we got it value as equation 4. Okay. So now we come back and substitute here. Okay. So what was our left hand side on this equation? This is a very important equation. This one. Okay. On the left hand side, we have to substitute equation 2, the value of equation 2, okay, the extension along dB. Okay, on the right hand side, you have to substitute the value of the equation 4. Okay, so I'm going to take the equation 2 and then substitute here. I'm going to substitute this equation 4 on the right hand side. So this is L by root 2. Okay. And then what was our second equation? What was our second equation? Our second equation on the left hand side was root 2. Okay. Into L, root 2 L, dB into T into alpha plus beta. Okay. Now, what is the ITL? Equation 1, we have started with finding the quantity is Ti. Equation or LTM was how much the cube has extended. Okay, the shearing strain has been studied in terms of the extension that it does. And okay, so find L. So one. Okay, so okay, our ATL by so before that, so our aim is to find L over here. So L is equal to, take it on the other side, it will become root 2 into root 2 will become 2. Okay, 2 into L into T into alpha plus beta. This both will become 2. Okay, so this is our extended length. Okay, we have found out one factor with respect to the linear strain, okay, and that of the lateral strain. Okay, Now we will come back to our original aim. What was our original aim? Our original aim was to find out the modulus of rigidity, and that is in terms of the extension along alpha and beta. Okay, so now come back to our equation 1. Okay. So the modulus of rigidity. Now we are going to connect all these things together with the modulus of rigidity factor. Therefore, the modulus of rigidity is given by, in our case, we have found out eta is equal to, remember the first equation, T into L by L. Okay. Therefore, substituting for L. Okay. Let me put this as equation number 5. Okay. So let me substitute. Okay. I have substituted the ultimate aim is this one. Okay. So now cancel out the common factors on numerator and denominator. So eta will become 1 by 2 of alpha plus beta. Okay. Now, as we did in the previous case, okay, divide the numerator and the denominator by alpha on both the sides. Okay. So let me divide this. Hope this is clear to you. Now, dividing the numerator and denominator by denominator. Let me write. By alpha. Okay. So eta will become 1 by alpha by 2 into alpha by alpha plus beta by alpha. Okay. Now, as in the previous case, I've already said 1 by alpha, nothing but the linear strain, is equal to this value, since we know 1 by alpha is equal to 1. Young's modulus. Okay. And this beta by alpha is nothing but, do you remember that it is the Poisson's ratio? Okay. So it will become, eta will become, this value will become now y, and this will 2 will remain the same. This will become 1 plus this factor is nothing but sigma, which is Poisson's ratio. Okay. Nothing but Poisson's ratio. No? So this will become sigma. So ultimately, we are getting eta is equal to nothing but y divided by, okay, y divided by 2 into 1 plus sigma. Okay. So now we have come to the conclusion. Now we have connected the modulus of rigidity with that of the Young's modulus and with that of the Poisson's ratio. Okay. This is clear to you. I hope this is clear. Go through the notes slowly and then study it. Okay. So this is a relation which connects the Young's modulus, modulus of rigidity, and the Poisson's ratio. Both, all the three are connected. Okay. So rigidity modulus, Poisson's ratio, and the Young's modulus are connected through this particular equation. Okay. So thank you so much for listening to this video and to listening to this class. Okay. See you all.